Let's now give a proper derivation of the multi-asset Black-Scholes PDE. We assume here that we have a asset price process, S, consisting of capital N many risky assets, S1 up to S capital N. We also have a capital N dimensional standard Brownian motion, which is a Brownian motion under the risk neutral measure Q. In that case, we model the dynamics of the underlying assets by the following SDE. dSt is equal to dSt rdt plus sigma tst dwqt. Here sigma is a n by n matrix process, which depends on time and the prices of the underlying assets. In particular, we don't assume that sigma is constant. R is the riskless rate, which may be stochastic, and dSt is a diagonal matrix with the asset prices S1 up to S capital N along the diagonal. In addition, we have a riskless bank account that satisfies the usual dynamics. In particular, the bank account process is a finite variation process. To simplify matters here, we will ignore dividends. Suppose now that theta is a self-financing portfolio. We've seen that in that case, the discounted value process of that portfolio is a Q martingale. Now let sigma n denote the nth row of the volatility matrix sigma, in which case sigma n dot sigma m, a dot product, is the same as the nm component of sigma times sigma transpose. Recall that the components of a standard Brownian motion are independent of each other. In particular, if we take a product dwqn, dwqm, we will get delta nm dt, where delta nm is the Kronecker delta. In other words, delta nm is equal to 1 if m and n are the same, and 0 otherwise. It follows therefore that if we expand the expression sigma n dwq, sigma m dwq, using all the possible components, we obtain the following result. Note that we only get contributions of the first term with the first term, the second term with the second term, etc., and that the cross terms all evaluate to 0. It is then easy to see that what we obtain is just the dot product of sigma n with sigma m, in other words, the nm component of sigma times sigma transpose. Thus, if we compute the covariation of the nth asset with the mth asset, we obtain the following. As usual, the dt terms, being finite variation processes, will contribute nothing to the covariation, and hence we're just left with sigma n Sn times sigma m Sm dt, as shown. If we now apply the Ito formula to Vt, we obtain the following. dVt is dV by dt dt plus dV by dsn dsn, summed over all n, plus a half times d squared v dsn dsm times the quadratic covariation of Sn with Sm, summed over all possible n and m. Now recall that dsn is just rsn dt plus sigma n Sn dw, and hence using the expression for the covariation obtained on the previous slide, we obtain the following expression. Let's now apply the Ito formula to the discounted value process. Recall that the discounted value process is just the value process divided by the bank account. Also, the bank account is a finite variation process. In other words, it will not contribute to any covariation terms, and hence by Ito's formula, d of the discounted value process is given as follows. Now on the previous slide, we worked out an expression for dVt, which is given by the expressions in this bracket here and this term here. Moreover, dAt is just r times at dt, and hence this expression here simplifies to 1 over at times r times v dt. As it is another dt term, we can incorporate this into this first bracket here and obtain the following. Now comes the crux. V bar, the discounted value process, is a martingale under Q and so has zero drift. In other words, this bracket here, the dt term, disappears. Hence, we immediately obtain the multi-acid Black-Scholes PDE. This is just the drift of V bar, which is zero. In addition, we obtain the dynamics for the discounted value process, which is given as follows. Note that here we have the discounted asset prices, but that this expression here is just the partial derivative of the value process with respect to the asset price, no discounting. Now suppose that theta is a replicating portfolio of a European-style contingent claim C. In that case, by the law of one price, C is equal to V for all times before the maturity of the option. And since V satisfies the PDE, so does C. The boundary condition for the PDE, in other words the terminal condition, is then determined by the payoff of the option. For example, an exchange option, which gives the right to exchange asset S1 in return for S2, would have the following terminal condition. In other words, the payoff is the maximum of S2 minus S1 and 0.